So on any part of this talk. Please, people, come forward with your questions. Don't be shy. I know it was crystal clear, but so I've got some, well, let me ask some questions. Regarding the work you've done on moire patterns, can this be studied in terms of homogenization as a specific case of cut and projection, these moire patterns, you know, or is it a totally different technique that would be used to homogenize these kinds of
That's a good question. So we did not use this here. Let me go back to that one. So what we used, we just used direct calculation, direct calculation of the spectral measure, but it would be really interesting to generate that as cut and projection numerically. So this direct calculation for these two-dimensional structures, this is numerically, this is very, very time-consuming and effort-consuming problem. So of course, if homogenized properties could be calculated using cut and projection, that would be much more efficient than using that. But here we had a different goal, so we did not calculate effective properties. We did not calculate homogenized properties. We wanted to calculate spectral measure and use the direct calculation of the spectral measure. But maybe if we can write that using cut and projection, maybe hopefully even the calculation of the spectral measure could be done more efficiently. I didn't think about that. This is a very good question.
In fact, in physics, this kind of structures are reminiscent of what they call twisted graphene.
Exactly.
So it's a really hot topic, actually, and this is
exactly. Yeah, exactly. These are very, very interesting structures. Exactly. Yeah.
And something crazy. Could you envision something similar, but in 3D, let's say? Could you have, you know, because here it's 2D, but with your kind of method, you could do perhaps something, I don't know, since it's based on some kind of interferences of plane waves.
Of course, because here the structure is generated by basically twisting one lattice or rotating one lattice with respect to the other, like in graphene indeed, two-layer graphene that you mentioned. But of course you can have lattice in 3 dimensions, and then another lattice or similar lattice, but just rotated.
Right. Exactly.
Exactly.
So you could imagine to have 2 cubic lattice, I don't know, rotated with respect to one another. But in this case, what's really funny is that you would combine 2 rotations. And we know that rotations, you know, they do not commute in 3D. So perhaps you would have very interesting properties, you know, by first rotating in one plane and the next, or the opposite. I mean, perhaps you would end up with very strange properties because of this non-commutativity of matrix, rotation matrix product.
That's right.
Perhaps something. Okay. People, please come forward with your questions. I mean,
can I ask a question?
Of course, Sasha, of course.
Hello, Lena. This is Sasha.
Hi, Sasha.
Just wanted to ask about the boundary conditions. So the homogenization of boundary conditions, even in the periodic case, sometimes is a challenge. But if you have quasi-periodic geometry, are there any constraints that you would need to impose on your boundary conditions, not only on the geometry, but also on the operator for this homogenization procedure?
Basically, the homogenization problem is formulated as a problem in higher dimensional space. So all periodic conditions that we have for periodic homogenization now are the same, but just in high dimensional space.
I understand that, but at the very beginning, you gave several examples of problems with the boundary conditions. And suppose you have a similar setup, but instead of periodic structure, now you have a quasi-periodic system, and you do have boundary conditions. So what do you do about these boundary conditions? And here, for example, you have Dirichlet boundary condition, but suppose you have a differential operator and you have Neumann or Robin boundary condition. What do you do in this case? What is the way to deal with boundary conditions when you apply the homogenization for quasi-periodic systems?
So that should work. So we can have Neumann or Robin in higher dimensional cell. So the problem, so why this is, we view this as an efficient way. So why this homogenized problem is interesting, I think, because it will allow us to efficiently calculate the effective properties. So we cut and project on this high dimensional cell, and this is basically, so what happens with the, so you have still on the boundary, no, it's still all the same because okay, it's like, okay, let me go back to this figure. So so periodic cell basically, so this just shows the high dimensional periodic cell and the cut and projection, right? So the boundaries of the cell are glued together. So this is the periodic, so this is, the cell is cell of periodicity. So we still in higher dimension, so this is our high dimensional cell. So we still have boundaries glued together. This is cell of periodicity, right? So the only difference is that now this cut and projection, it covers the whole surface of the cell.
Well, I have no problem with the case when you have infinite space covered in the periodic pattern in a higher dimension, and then you use the cut and projection method. It's all clear. It's all good. I'm perfectly happy. It's really interesting. It's great. But I'm thinking about the case when you have a finite domain, so you have a microstructure, and then you have a boundary, or you have oscillation on the boundary. And of course, there are well-known examples when homogenization of the boundary condition has to be used with care. For example, you can take the babushka paradox when you take a polygonal plate and look at the limit and compare with the circular plate, and you don't really get matching results. So I'm thinking about the domain with a boundary, and the question is, are there any constraints? I'm sure there are, but I simply don't know what they are, and that's really the question. If it's too much, please don't worry. But I was just thinking that this can be a really interesting challenge.
Okay, I agree, Sasha. I completely agree. That problems arising around the domain. So if I have a domain field with quasi-periodic material, then there will be some problems about the boundaries, of course. And actually there are some works that show that some quasi-periodic structures arising along the boundaries in homogenization, but here we don't consider that. This is a different question. Yeah, this is a different. Yeah.
Okay, so, I understand. Okay, thank you.
Sure, but this is a very interesting question. I completely agree.
Thank you.
But
Thank you,
just different. I'm not sure. We probably need something different to address that.
All right. Thank you.
But if I'm not mistaken, Elena, we just need to assume that the boundary of the quasi-crystal is regular, and then I think we are good with this case. We can treat finite crystals. I think provided it's Lipschitz or regular enough. If I'm not mistaken, the two-scale homogenization works well. Because in fact we don't proceed with higher order terms in the asymptotic expansion. If we would add higher order terms, then we would have some problems with the boundary. But here, since we stop at the U1.
That's right. But that's the problem, I think, because for finite size crystal, we would need higher orders because that's exactly as with periodic homogenization. When we consider periodic homogenization and send the size of the cell of periodicity to 0, so this is asymptotic expansion. So this is equivalent to zooming or blowing up the vicinity of the point of interest to infinity, basically, so that it's like a periodic infinite medium without the boundaries. So boundary conditions on the cell of periodicity. These are different from the boundary conditions on the domain that we consider. If we consider finite domain field with material, so there might be something we would need to take care of.
Excellent. Do we have any more questions related to the theoretical or practical aspects of the talk?
I have a question.
Yeah, sure. Please
do. For the Moiré pattern study, did you also look at translations? Is it just rotations or is also translations? And rotations and?
No, this were rotations and scaling.
And scaling.
Scaling.
Okay.
Hmm.
So why not translations? It's
Oh,
like
that's already so rich class of structures that generated so many interesting phenomena. So we didn't think about translations, but maybe also because, as Sebastian mentioned, the graphene is just these are two hexagonal structures just rotated. Two hexagonal lattices. One is just rotated with respect to the other one. But generally more patterns certainly even like this is amazing way to create structures. Yeah. So translation, if to add translation, then maybe it would be another interesting aspect, as well as three-dimensional with three-dimensional lattices. That should produce something extraordinary, I would say. But I'm not aware of any three-dimensional Moore patterns.
But really, the principle should be the same, no, guys? No, just you can rotate this with respect to one another. No, you can imagine this, no?
Yeah, certainly, of course. Why not? If there is a lattice in 3 dimensions and we rotate it at some angle and combine with the original lattice, yeah, but it's hard to imagine because it is hard to imagine because we will have interference not only in one plane. So these Moore patterns, they are basically like created by interference of these two lattices, one rotated with respect to the other one, and now in three-dimensional space one can have 3 planes and interferences in each of these planes and interference between them. So that might be very interesting. Yeah.
Do we have any more questions regarding, for instance, inverse problems? So, in fact, what are the well-known results regarding, let's say, the Bergman-Milton theory of bonds if you have quasi-crystal phases? You know, quasi-crystalline phases. So what would be so are there any results from Golden, or I mean, so you consider the Milton-Bergman theory of bonds, so you have conductivity problem, but it's quasi-crystals. How would that work? I mean, can you just imagine what would happen to these bonds? I mean, so you have a mixture of two media, but you know that it's a quasi-crystal. Well, you know, there is no periodicity, but it's quasi-periodic. So of course, this is a special case, perhaps, of random, no? So it should fall within the theory of bonds for random media, at least, no? I mean, it's some kind of...
Exactly. So Bergman and Milton, they formulated that representation for just for periodic case. Basically, Bergman wrote that down for a periodic case, and then Graham noticed that so in periodic case, this representation is just given by a sum. So so instead of the integral, there is a sum, and mu. So in periodic case, mu could be represented. The spectral measure mu is represented as a set of delta functions. So delta functions corresponding to the resonances. So all this integral reduces to a sum, and then Graham Milton noticed that that should not be a sum, because even some composites are known when the effective property is given, should be given as integral, and that example is given by checkerboard structure. So for the checkerboard structure, the effective property of a checkerboard composite is given as square root of epsilon1 times epsilon2. This is known. This is the result known. Dichner, yes, exactly. And this could be transformed to that plane S, this plane of complex variable S, but still there is a square root. So so not only there will be, so it's not like a rational function. So mu is a square root function, or it could be written as some density times dz, but there is a square root, so one cannot just immediately write. So this representation should be not a sum. This is integral for the checkerboard.
Okay.
And actually then after that, Ken Golden and George Papanikolaou, they wrote that for random media.
Yes.
So that's just completely random case with some probability measure given on a set of realizations. So quasi-periodic case, okay, of course, quasi-periodic could be, or periodic or quasi-periodic, they could be considered as particular cases of random composites, stationary, no boundaries. Again, back to Sasha's question. But there's nothing specific about, so the problem is that okay, so this representation was used to draw the bounds, the set of bounds on the complex plane, to bound the effective property, to bound the effective complex permittivity that could be obtained mixing two materials with permittivity epsilon1 and epsilon2, and these bounds depend on the particular information. For instance, for isotropic composites, we can, and these bounds, they are kind of like length shape given by length shape. I don't know if I can draw here.
Everyone can see the screen, by the way. For me, it appears white. You can see what's on the screen of Elena? Fernando, yes? Okay, it's just my editors. And okay, good.
No, I cannot. It looks like I just can't write can draw a only I can draw only straight line. Well, anyway, so no, okay. So the bounds look like lens-shaped domains on the S plane, and that could be like using this transformation back could be mapped to the complex permittivity plane, just to the frequency domain.
Okay.
So if you know, for instance, if you know that these materials are the obtained composites are periodic, not periodic, isotropic, then the bounds reduces to much smaller, again, lens-shaped domain, but much smaller lens-shaped domain. So if you know that the composites are quasi-periodic, then of course we should be able to use this in the representation and in the bounds. So that's why this representation that this analogous Stieltjes analytic representation with this spectral measure of the quasi-periodic operator gamma, so this gamma sub r chi, this will allow us to draw the bounds for the effective properties of quasi-periodic composites. So we hope that this will be a very efficient way to bound the properties using this.
So in fact, then it would be a sharper estimate than given by the bounds for random media.
Right,
it will
right.
be more specific to, okay, this,
Right,
okay.
right, exactly.
And possibly this estimate, depending upon the irrational slope, will vary between the estimate for periodic and random media. Perhaps depending upon the degree of irrationality of the slope, perhaps it will.
Right.
No, it would.
Right.
Generate a whole class of bounds depending upon the degree of irrationality of the cut for the.
That's right.
Perhaps. Okay. Do we have any more questions in the audience? I mean, this is fascinating because I can see that in Utah, you have results which range from theory to, experiments. So you theory, numerics, experiments, and you also build upon many years of work on this composite. So it's quite nice, I think.
Yeah, we have very nice group. And Fernanda is going to talk about this ultrasound
Totally.
assembly. Yeah, ultrasound driven patterns. Yeah.
And you mentioned in passing at some point that quasi-crystal have very strange mechanical properties, like for friction, like for adhesion, and so on. So do you look also in Utah in the mechanical engineering department at this kind of mechanical properties, or not yet? I mean, I guess
not. I do not know if someone is.
It's funny because our collaborator on this,
yes.
so it's battery makers, he also works on tribology, which is looking at the friction between two different surfaces. And then, like for example, when you have implants, you want to make he's designing like micro patterns on the implant so that there is less friction or something like that. So, but I don't think they've considered quasi-crystals, but it would be a good thing to consider, I think,
Yeah,
the same reasons. So,
Excellent.
that would be.
So
We have
actually,
someone.
Yes, sorry.
We have someone in physics, Orest Simko, who created these quasi-periodic structures. Actually, I think I have one of the pictures from his website. This one. We also have Will Feldman, actually, in math department, who studied these quasi-crystals, and so they showed that so they studied that contact angles, and they showed that it's really like even bigger than, say, Teflon contact angle.
Okay, it's regarding this droplet on the quasi-crystalline surface. Okay.
Yes.
I remember. Okay, fantastic. Really, it's amazing research, and thank you so much, Professor Cherkaev, for this wonderful talk. So like you mentioned, in 2 weeks, we'll have bis repetita with more info. So I would like to thank you again for this wonderful presentation. And next week, we should have Tim Starkey and Professor Alastair Ibbins from Exeter University, who will give some talk on acoustic metasurfaces. So we will go back to the periodic world next week. Okay, thank you so much, everyone, for staying with us. And do not hesitate, by the way, to drop us an email, or to, of course, to Professor Cherkaev if you have any more questions, or you would like to propose, to suggest speakers for the next season, which will start in September. Bye-bye and stay safe.
Bye-bye. Thank you.
Bye, Fernando.